Let's study 9th Standard ICSE Physics, Chapter 10, Magnetism. Section A, Induced Magnetism and Neutral Points. Now, if you take a magnet, say a bar magnet with a north pole and south pole, and hang it by a silk thread or any other string, and just let it come to rest, you will notice that it always rests in the north-south direction. That means the north pole is in this direction and the Earth's south pole, geographic south pole, is in this direction. That's because Earth has its own magnetic field which affects any suspended magnet. Magnets could be naturally found. For example, a triferric tetroxide or magnetite has magnetic properties. They can also be artificially made, for example, electromagnets. Magnetism can also be induced in an iron or steel bar. Such magnetism is called induced magnetism. Let's see how it works. Iron or steel bar is not a magnet on its own, as in it doesn't attract iron filings towards itself. However, in the presence of another magnet, it starts behaving like a magnet because it believes in the dictum, when in Rome, behave as Romans do. So, in the presence of a magnet, it develops a north pole and south pole. And so now it will attract the iron filings. But this is temporary. If you remove this magnet away, this bar will stop acting like a magnet. The north pole and south poles will disappear and the iron filings will fall down due to gravity. And notice that if we keep the south pole of the magnet nearer to the bar, then this nearer end develops an opposite polarity, north pole. It's always opposite. If we would have kept the north pole of this magnet closer to the bar, then this end of the bar would have been south. And that is why even this iron bar is attracted towards the magnet. We know that magnets attract iron, cobalt, nickel and other magnetic substances like steel. But how does this attraction work? Well, induction precedes attraction. What that means is, we know that two magnets may attract or repel each other. If you bring the south pole of a magnet close to the north pole of another magnet, they will attract each other because unlike poles attract. But if you would have brought like poles together, like south and south or north and north, they would repel each other. But why does an iron bar get attracted to a magnet? Because as soon as you bring a magnet near it, and remember this magnet has a magnetic field all around it, which we can't see, but it influences this iron bar and induces magnetism in it. So it starts behaving like a magnet. And now that we have opposite polarity, south and north pole, they will be attracted towards each other. Of course, if this bar is very heavy, it won't move. But if it's light enough, you would actually see the iron bar moving towards this magnet. And the same logic applies to answer the question, why are the iron filings getting attracted? Even if this bar became a magnet, why is the iron filing getting attracted towards it? Because now the iron filing is acting like tiny magnets. Even they have a north pole and south pole. Let's understand this with the help of iron nails. So if I have a bar magnet, this is the north pole. In its presence, iron nails near it would become tiny magnets themselves. This is called induced magnetism. And of course the nearer end will become the south pole and the farther end will become the north pole. So that is induction. And now that they have opposite polarity, there will be attraction. That's the whole meaning of the sentence, induction precedes attraction. The iron nail is not attracted straight away. First, there should be an induction and it should be converted into a magnet. And then because of opposite polarity, there is attraction, which takes a fraction of a second, of course. Not only that, now since this is acting like a magnet, it will induce magnetism in the next nail. And the process goes on. And you get this chain of nails being attracted to the bar magnet, all with opposite polarity, one after the other. Of course, this will not go indefinitely. A point will come when the weight of the nails becomes so much that the magnetic force is unable to hold it against gravity, and it will fall down. Also note that if you just hold this first nail with your fingers, and with the other hand, you take away this magnet, all the nails would come tumbling down, and all the queen's horses and the king's men wouldn't be able to put the nails in order back again. This proves that this induced magnetism is temporary. So this can be asked for 2 marks each, either induction precedes attraction, explain, or an experiment to prove that it's temporary. You're supposed to read the entire textbook here. I'm just explaining the concepts. There are a few definitions. Definition of induced magnetism: the temporary magnetism acquired by a magnetic material when it is kept near or in contact with the magnet is called induced magnetism. You can't miss a single word in any definition. Brackets are also important. Even words like temporary, if you miss it, you get 0. Next, what is magnetic induction? Well, that's the process which produces induced magnetism. So even that is a definition you need to study. Next, we move on to the topic called the lines of magnetic field. Here the meaning of vicinity is neighborhood area. Now, we know that every magnet has an invisible magnetic field around it. It's not a real line. It's something we use to represent the magnetic force acting around it. It's a very useful tool. Fields are used for other forces also, for example, gravitational fields and electrostatic fields, etc. One way to visualize these fields is take a very strong bar magnet, put a thin white cardboard on it or a white paper, a stiff one, sprinkle some iron filings on top of it, gently tap the white stiff sheet. You will notice that all the iron filings arrange themselves in a particular structure which looks like this. Notice how the magnetic field lines are curved lines from the North Pole to the South Pole. Not exactly from the North Pole here, it could be from here as well. We also see these lines which don't seem to be coming or ending at the bar magnet. Well, these faraway lines are actually Earth's magnetic field, because Earth also has a magnetic North Pole and a magnetic South Pole. More about it shortly, but now we can define a magnetic field of the magnet. You can see that the effect of this magnet will be in the nearby area. Theoretically, magnetic fields stretch up till infinity, but as you know, as the distance increases, the strength of the force decreases rapidly. That means beyond a certain distance, this magnet will have no influence. Even the Earth's magnetic field has limitations beyond a few hundred kilometers. So, the definition: the space around the magnet in which the needle of a compass rests in a direction other than the geographic north-south direction is called magnetic field of the magnet. Let's understand this with the help of diagrams. Now imagine this is the Earth. It has a geographic North Pole and South Pole. It rotates about this axis. Earth also has its own magnetic South Pole and magnetic North Pole, because you can imagine the Earth's core acting like a magnet because of some nuclear reactions and other phenomena happening inside. So Earth has its own magnetic field around. We can't see it, of course, but it can easily be detected. This magnetic field is very different from the atmosphere. Okay, atmosphere is made up of air. The magnetic field is a force field. It's totally different from the atmosphere. Now, if you look at a very small region of the Earth's magnetic field at any place on Earth, apart from the poles, of course, you will notice that it is like 3 parallel lines which are equidistant from each other and parallel to each other. That is why in a very short region, small region on the Earth, we can imagine the Earth's magnetic field to be uniform, like this. And of course, the arrows mean that the force is acting from the North Pole, magnetic North Pole, to the magnetic South Pole. That's the rule for any magnetic field line. It's a vector quantity. So its direction is always from the magnetic North Pole to the magnetic South Pole. I'm stressing on the word magnetic pole because that's a little different from the geographic poles. It's not even coinciding. And another surprising thing is that the magnetic North Pole is actually near the geographic South Pole, which makes sense. If you have a compass, why does the North Pole get attracted towards the geographic North Pole? The magnetic compass always points north, because this magnetic needle's North Pole is getting attracted towards the Earth's magnetic South Pole. Unlike poles attract each other, right? If this was the magnetic North Pole as well, then there would have been repulsion, not attraction. So because Earth's magnetic North Pole is to the south, that is why the compass points like this. That's how the compass works. So these are the magnetic field lines from north to south, and hence it is pointing towards the Earth's magnetic South Pole, which is geographic North Pole. And that is why magnetic compass is useful in knowing the direction. So make sure you're very clear about the fact that the magnetic poles and the geographic poles are different entities. In fact, the magnetic pole's position keeps changing every year by a few millimeters. Over thousands of years, the North Pole and the South Pole may be near the equator, or there might be a pole reversal. That would be quite disastrous for all our satellites and technology which is based on the Earth's magnetic field. But no need to worry as of now. This magnetic field has another advantage. The rays from the sun may be of electromagnetic nature, or they may be cosmic rays made up of particles. The high velocity particles are quite dangerous. They can cause a lot of skin diseases and they can harm our organs if they hit our body. But thanks to this magnetic field, they are deflected. So it prevents us. Just like the ozone layer of the atmosphere protects us from sun's UV rays, similarly the magnetic field saves us from the sun's harmful radiations, ionic radiations. In fact, when these ions are passing through the magnetic field, it ionizes the atmospheric molecules and it gives you a very colorful sky, which is called aurora, which you can see in regions near the North Pole and the South Pole, like in Australia, Netherlands. The sky looks like this, so colorful. Really, it does. You'll have to visit some Scandinavian countries to see this spectacle in the sky. So the fact that any bar magnet always points towards the north, or the magnetic compass points towards the north, or we can see the auroras, this is all evidence that Earth has a magnetic field. However, if we have another bar magnet near this magnetic compass, and it disturbs the orientation of the magnetic needle in the compass, then that means that the magnetic compass is in the influencing region of this bar magnet, and that region is called the field of the magnet. If it is far away, it won't be affected by this magnet and it will continue to point in the north-south direction, or rather north direction. So it is outside the field of the magnet. So now you understood the definition of magnetic field of a magnet. Theoretically it's infinite, but practically it is strong enough only to a certain distance. Now let's define a magnetic field line. A field line is a continuous curve, there are no breaks in between, it's a continuous curve in the magnetic field such that the tangent at any point of it gives the direction of the magnetic field at that point. Now, we know how to visualize a magnetic field using iron filings, but there is another way to see the magnetic field. Imagine that I keep my compass, magnetic compass, out here, and the needle points in this direction. So let me just put a point out here. Next, I keep my compass out here and the needle points like this. Obviously, North Pole and North Pole will repel each other, so it will be pointing towards the South Pole. Let me put a point here. And I keep on doing it at various places. And in the end, if I jot down all the points and I connect it, it would look like this, which gives us the magnetic field line. So if I draw a magnetic field line, this means at any point, say out here, if you want to know the direction of the magnetic field, just draw a tangent to it. Tangent is a ray, a line, which touches the field line only at one point. So if there is a circle and I want to draw a tangent, this is a tangent. This cannot be a tangent because it is touching the circle at 2 points. But if it is touching only at one point, it is called a tangent. If you ask me, what is the direction of the magnetic field out here? Well, I would say this is the direction. See, the direction keeps on changing at each and every point because the direction is always from the North Pole towards the South Pole in a curved path. What's the direction at this point? Then I would say this is the direction. So this magnetic field line is actually helping me to understand the direction of the magnetic field at each and every point around the magnet. So now I know that if I keep a magnetic compass out here, in which direction will the needle point? Definitely like this, along the magnetic field line, which is the direction of the magnetic force acting. So now you know the definition of magnetic field line. Next, there are some 7 properties of magnetic field lines. So let's study them. Number 1, they are always closed and continuous curves. They are not open curves. You will never see an open end. Second, they are always starting from the north and ending to the South Pole. But inside, it continues, right? It's supposed to be closed. So this will continue and close the loop. So inside the direction is from South Pole to North Pole. Outside the direction is from North to South. Inside the direction is from South to North. So that's a continuous closed loop. Third point, the tangent at any point in a field line gives the direction of the magnetic field at that point, which I just showed in the diagram. And fourth point is an important GR. No two lines can intersect each other. If you draw another magnetic field line like this, well, that's wrong. That's not possible. Two field lines cannot intersect. Think about it. If this was possible, and I ask you, what is the direction of magnetic field at this point? You could either say this is the direction, or you could say this is the direction. How can a force have two directions at the same time? So, two magnetic field lines cannot intersect each other. That's not possible. Fifth, the lines are always crowded near the poles, and they are a little far away in the center of the magnet. As you can see here, near the poles, the density of the magnetic lines is more because it's more powerful here. And in the center, they are a little far away because the magnetic field is weak. And as you go far away from the magnet, again you will find that the distance between the magnetic field lines is increasing, which reflects the weakening of the magnetic force. Even if you bring this near a lot of iron filings, you will notice most of the iron filings stick at the north and south pole, and very few stick in the center of the magnet, which is the weakest area of the magnet. But note that actually the north pole is not exactly at the tip, or south pole is not at the tip, it is somewhere here. Sixth point, parallel and equidistant field lines are called uniform. For example, Earth's magnetic field in a limited space. So I had shown this in a very limited space. If you zoom in, it looks as if they are parallel to each other and equidistant from each other. And also magnetic field lines behave like stretched elastic rubber strings. Field lines are not a real thing, it's an imaginary thing, but when you bring two magnets together, the shape of the magnetic field changes as if they are made up of rubber strings. Look at these diagrams, which you have to practice. First diagram is straightforward. It's always from the North Pole to the South Pole. What if it's a horseshoe magnet? Well, again, it's from the North Pole to the South Pole. Yeah, some of them are going from North Pole to the Earth's magnetic South Pole, or coming from the Earth's magnetic North Pole to the magnet's South Pole. But what if we have two magnets and we bring the unlike poles together? Again, the field lines are from North Pole to the South Pole, and that's why they get attracted to each other, because it's like a stretched rubber band. The stretched rubber band always tries to shrink, isn't it? So these lines would like to shrink by bringing the two poles or two magnets together. On the other hand, if you have like poles, then see, the lines cannot intersect each other. So they just try to avoid each other. There is repulsion between them. In fact, there will come a point in the center where the magnetic field of this magnet and the magnetic field of this magnet are equal and opposite to each other. So they will cancel each other out, and that point will be called a neutral point. Which means if I put a magnetic compass out here, it will not be influenced by either of the magnets. It would be as if there are no magnets out here. It would now only be influenced by the Earth's magnetic field, and the magnetic needle will point perfectly towards the Earth's North Pole. It won't be affected by these two magnets if they are equal and equidistant from each other and from the magnetic needle. Now let's look at the evidence of existence of Earth's magnetic field. First, a freely suspended magnetic needle always rests in geographic north-south direction. Even if you just give it some push and let it come to rest, it will come to rest in the north-south direction, assuming that there is no other magnet nearby. Second, if you bury an iron rod inside the earth along the north-south direction, after a few days, you will notice that when you remove the iron rod, it starts behaving like a magnet. So magnetism has been induced in the iron rod. But who did that? It has to be the Earth's magnetic field. Third evidence is that often we find neutral points when we are plotting the field lines of a magnet. But if I have a magnet and I find that there is some point near it where it doesn't have any magnetic field, that means some other magnetic field has cancelled the bar magnet's magnetic field. What could that some other magnetic field be? It has to be the Earth's magnetic field. We'll study neutral points in detail soon. And the fourth evidence is a magnetic needle rests with its geometric axis, making different angles with horizontal when suspended at different places on the Earth. Let's understand this with the help of a diagram. If you have a freely suspended magnetic needle not in a magnetic compass, okay, it's freely suspended with the help of a string, you will notice that at the equator, it rests horizontal to the ground. But as you move towards the South Pole or the North Pole, imagine this is the needle, okay, it is horizontal. But if I'm at the poles, it is tilted towards the earth, or it is tilted away from the earth. So that means something is influencing it. If there was no magnetic field, it would have remained horizontal everywhere on earth due to gravity. But near the North Pole or near the South Pole, why is it not resting horizontally? Why is it getting tilted? That means there is some magnetic force of the earth acting on the needle. In fact, at the South Pole or at the North Pole, it is vertical. It rests vertically. And at the equator, it is horizontal. So this is another evidence of it. This is a good reason about neutral points. Why are they formed? And we have a couple of definitions here. The Earth's magnetic poles and the Earth's magnetic equator definitions. Remember, magnetic poles is different from geographic poles, and magnetic equator is different from geographic equator. As you can see, there is a slight angle between them. This diagram also has to be practiced. Lines of uniform magnetic field of the Earth. So finally, we come to neutral points. Now there are two diagrams which are very important. One of them will surely come in the exam. They are neutral point diagrams. I will show you a simplified version of this now. First of all, let's revise what is neutral point again. Neutral points are the points where the magnetic field of the magnet is equal in magnitude to the Earth's horizontal magnetic field, but in the opposite direction. So the resultant or net magnetic field at the neutral point is zero. Simply speaking, the bar magnet's magnetic field is neutralized by the Earth's magnetic field at a point. So overall, there is no magnetic field left at all. What this means is, at that point, if I put a magnetic compass, the magnetic needle won't rest in any specific position. It can rest in any position, as if there is no magnetic field available at all, not even Earth's magnetic field. Because the Earth's magnetic field has been nullified by the bar magnets or vice versa. Yeah, we talk about the Earth's horizontal magnetic field because Earth's magnetic field is actually three-dimensional, but here we are drawing a diagram in a 2D, on a 2D paper. So let's see how to draw this. Note that in this diagram, the bar magnet's north is facing towards the geographic north of the Earth. And in this diagram, the bar magnet's south pole is facing the Earth's geographic north. So in the diagram, this direction of Earth's geographic north has to be shown. Now imagine that Earth's geographic north is here, north, and this is the south. Now ideally, Earth's magnetic field is like this. It's uniform. It's always moving from Earth's magnetic north pole to magnetic south pole. Understand that this is the geographic north, but it's magnetic south pole, and the magnetic field lines are always from north to south. Here, let's place a magnet. Now this will have its own magnetic field which will disturb these lines of Earth. Let's keep the magnet in such a way that the north pole is facing towards Earth's magnetic south pole, or you can say the north pole of this bar magnet is pointing towards Earth's geographic north. This is the south. So its magnetic field will be like this, from north to south. So notice that the direction is downwards here, and Earth's magnetic field was going upwards. So they are quite opposite to each other at certain points. And at any point, the magnetic force or magnetic field will be a combination of both the magnetic fields, a resultant of the Earth's magnetic field as well as the bar magnet's magnetic field. So now let's draw the diagram for that. So we draw a bar magnet, use a ruler, the north pole and south pole. Near the magnet, the magnetic field of the magnet itself is strong enough. The Earth's magnetic field doesn't matter, it's quite weak actually. This bar magnet is stronger near the magnet. Just draw a couple of curves on both the sides. A couple of them is enough. Make sure it's symmetrical, not asymmetrical like this. I don't have enough room to move my hand, hence it's not coming out beautifully. Otherwise, I'm a great artist. What about the Earth's magnetic field? Well, little far away from the magnet, the Earth's magnetic field was supposed to be just a straight line. But as it is influenced by this magnet, now it will be a little curved as well. So it will go like this. This is from the Earth's magnetic north pole to the Earth's magnetic south pole on both the sides. So just draw a couple of lines for the Earth's magnetic field. And here, show a few of the field lines moving towards the Earth's poles as well. This is going towards the Earth's magnetic south pole, and here it is coming from the Earth's magnetic. If your arrows are wrong, you lose marks. So a couple of lines here. That's enough. Now, what is special is, look at this point out here. And this point out here. It's almost cutting the magnet into two parts. Imagine that the bar magnet's magnetic field was supposed to be like this, right? But the Earth's magnetic field is like this. So that means at this point, the bar magnet's magnetic field is in the south direction, and the Earth's magnetic field is in the north direction. So they are already opposite to each other. And what if they are equal to each other as well? Then they will cut each other. They will cancel each other. So at this point, there will be no magnetic field. So I'll put a cross out here, and that is called a neutral point. Yes, even here, if you notice that the Earth's magnetic field is opposite to the direction of the magnet's magnetic field, but here the magnet's magnetic field is stronger. They're not equal, so they don't cancel each other. But as you go far away from the magnet's magnetic field becomes weaker and weaker, and there will come a time when the Earth's magnetic field and the magnet's magnetic field are equal in magnitude, and they will cancel each other. Farther away, then the Earth's magnetic field will dominate. This magnet's magnetic field is irrelevant far away, so forget about that. So only at a particular point here and a particular point here will you have neutral points. If you keep a magnetic compass out here, it will point like this. If you keep a magnetic compass, the needle will point like this. But if you keep it at the neutral point, it will point in any random direction. If you shake it and keep it, again the direction will change, because effectively there is no magnetic field out here, which is quite surprising. Everywhere there is Earth's magnetic field, but at this point the Earth's magnetic field has become zero resultant because it was cancelled by the magnet's magnetic field. So now you know what is a neutral point. So remember, in this diagram, the neutral points are towards the west and east of the magnet, and they're equidistant of course. So this is how you'll draw a simplified diagram. And now the next diagram. So this time we'll draw a magnet, again a bar magnet, but we'll keep the magnet's north pole facing the Earth's magnetic north pole, or the Earth's geographic south. Let's show Earth's directions out here, north and south pole. So near the magnet, of course, the magnet's magnetic field is dominating. Earth's magnetic field is weak comparatively. So we'll just draw from north to south and north to south. A couple of curves are enough. Arrows, of course. Far away, if you go to see, the Earth's magnetic field is supposed to be from the magnetic north to the magnetic south. But because of the magnet, it will be affected. So now it will be like this. It will be like this here. That's the Earth's magnetic field. Now, there will come a point where this magnet's magnetic field is somewhere like this. Okay. So here the direction is like this. It's emerging from the north pole of it. And the Earth's magnetic field is coming from its magnetic north pole. So there will come a point where not only are they opposite to each other, but also equal to each other, and they cancel each other out. So that point will be called a neutral point. Here and here both. So notice here the neutral points are not towards the west and east. Here they are north and south of the magnet. And just draw a couple of rays. That's it. No need to draw so many rays, but let it be symmetrical, neat, with arrows, with all the directions written. And with that we finish this chapter. Make sure you read everything thoroughly and ask me your doubts during the lecture. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.